We've learned that we can use parametric equations to describe motion and direction on a graph. Now we're going to bring calculus into the picture. When curves are defined in terms of a parameter like t, how do we find their slopes, their tangent lines, and their arc length? We'll see that we can't just use dy dx, but if we chain everything through t, we'll be able to develop an understanding of these familiar topics. When we wish to find the slope of a tangent line of a curve that's defined parametrically, we have to remember that that tangent line's slope is still defined in terms of y and x. The slope is still going to be the ratio of the change in y to the ratio of a change in x. A simple application of the chain rule allows us to extend this then to find the derivative. We can see that dy dx, the ratio we're looking for, is equal to dy dt divided by dx dt, which we can write as g prime of t over f prime of t, when x is equal to f of t and y is equal to g of t. Let's take a look at an example. Here we want to find the slope of the tangent line and the equation of that tangent line for a curve defined parametrically, x equals t squared minus 1 and y equals 2t plus 3. We want those specifically when t is equal to 2. So if we look at this, we can see that dx dt is going to be 2t, and dy dt is going to be 2. If we put those together, we see that dy dx is dy dt over dx dt, which is going to be 2 over 2t, which we can simplify to 1 over t. Then in particular, dy dx, when t equals 2, is going to be 1/2. So now we have the slope of our tangent line. We need an equation, but of course to write the equation of a line, we have to have a point on it. So to find the point, we just use the fact that t equals 2. We know that x was t squared minus 1. So when t equals 2, x is going to be 3. And we know that y was 2t plus 3. So at t equals 2, y is going to be equal to 7. So now we have a point on our line. We have the point 3, 7. And we have the slope of 1/2. So our tangent line is going to be y minus 7 equals 1/2 times x minus 3. And if we wish to write that in y equals mx plus b form, we can do so. We get y equals 1/2 x minus 3/2, which is y equals 1/2 x minus 3/2 plus 14/2 gives us positive 11/2. Let's look at another example. This time we're going to find where the curve defined by x equals 4 cosine t and y equals 16 sine of t for t between 0 and 2 pi has horizontal and vertical tangent lines. So let's start with dy dx. dy dx, we know that's going to be dy dt over dx dt. So dy dt, the derivative of y equals 16 sine t, is going to be 16 cosine t. And the derivative of 4 cosine t is going to be negative 4 sine t. So we can see that this simplifies to be negative 4 cosine of t over sine t, which of course we can write as cotangent if we want, but I think we're going to see in a moment that it's easier to actually leave it in this form because dy dx equals 0 when negative 4 cosine of t is equal to 0. In other words, when its numerator is 0. But we know that between 0 and 2 pi, the cosine is equal to 0 at pi over 2 and 3 pi over 2. So we have the t values where that happens. Let's go ahead now and find the actual x and y values. So we know that x is 4 cosine t, y is 16 sine t. So when t equals pi over 2, x is going to be 4 times the cosine of pi over 2, which is 0, and y is going to be 16 times the sine of pi over 2, which is going to be 16. So our first horizontal tangent line, where the slope is 0, is going to be at the point 0, 16. And then we can do the same thing for 3 pi over 2. The cosine of 3 pi over 2 is 0, so we get x equals 0 again. But the sine of 3 pi over 2 is negative 1, so we get negative 16 as our other horizontal tangent. Now we can do vertical tangents. We know that dy dx is going to be undefined. That's where we have a vertical tangent line when the slope is undefined, when the sine of t is 0. So on our interval that occurs at t equals 0 and at t equals pi, we don't need to include 2 pi because the values we're going to get, because of the period of both these functions, the values that we're going to get will be the same for 0 and for 2 pi. So now we just find our points. Again, we're looking at x is 4 times the cosine of t and y is 16 times the sine of t. So when t equals 0, we get x is 4 and y is 0. So we have one horizontal tangent at the point 4, 0. And then when x is pi, we get when t is pi, we get that x is negative 4 and y is once again 0. So we have another one at negative 4, 0. So we have vertical tangent lines at 4, 0 and negative 4, 0. Another application of calculus to parametric curves that follows pretty straightforwardly from what we know about non-parametric curves is the idea of arc length. So if x is equal to f of t and y is equal to g of t, where the derivatives are continuous and we're only traversing the path once from on some interval from a to b, then we can define the length of that curve, which starts at the point f of a, g of a, that's an xy value, and ends at f of b, g of b. That's going to be given by the integral from a to b of the square root of f prime of t squared plus g prime of t squared dt. Let's relate this back to what we know about the length of curves that are defined in the typical Cartesian manner. So if we know that y is some function of x, then the length of the curve from f of a to f of b is going to be given by the integral from f of a to f of b of the square root of 1 plus dy dx squared with respect to x. But here we know that x is f of t and y is g of t, which means that dy dx is going to be g prime of t over f prime of t. It also tells us that if we look at this, we see that dx dt is f prime of t, so that dx is the same thing as f prime of t dt. So we can do some replacement here. We know that f of a and f of b, if we switch to the variable t, right, these belonged to x. If we switch everything to t's now, if we go t is equal to a and t is equal to b, this becomes 1 plus dy dx is g prime of t over f prime of t squared, and dx is f prime of t dt. So we've now rewritten the entire original expression that we knew from finding arc length of Cartesian curves We've now converted it to one that only involves t, and then we can just do some algebraic simplification. If I get a common denominator in here, I end up with f prime of t squared plus g prime of t squared all over f prime of t squared times f prime of t dt. But this right here, since it's sitting inside of a square root, we can pull it out by square rooting it. So we get the integral from a to b of the square root of f prime of t squared plus g prime of t squared over f prime of t, again pulling that out of the square root, times f prime of t dt. And now we can see that these f prime of t's cancel, and we do in fact get the exact formula that we started with, the integral from a to b of the square root of f prime of t plus g prime of t dt. And so, without passing back through an unparameterized curve, we can now find the arc length of a parameterized curve. So let's take a look at a couple of examples of that. One really nice application of this is that we can use it to confirm a formula we're probably pretty familiar with, the circumference of a circle. So if we want to find the circumference of a circle with radius a, we know that we can parameterize the circle. We can do that using the equations x is equal to a times the cosine of t and y is equal to a times the sine of t. And what we're doing here is we're assuming that we've positioned our circle so that its center is at the point, as at the origin, is at 0, 0. This becomes slightly trickier if we move the circle around, but of course to confirm its circumference, it doesn't matter where we position it. So we'll use the convenient location at the center. And now, given that, we know that the circle goes from t has to go from 0 to 2 pi in order to complete the entire circle. So the arc length of this curve is going to be the same as the circumference of the circle. And we know the formula for arc length is going to be the integral from 0 to 2 pi. And then we're going to take the square root of the derivative of x. So if x is a cosine t, we know that f prime of t is going to be negative a times the sine of t. So we get negative a sine of t squared. And then if y is g of x, g prime of t is going to be a times the cosine of t. So in here we'll get plus a cosine of t all squared, and that's with respect to t. So just for clarity here, I'm letting x be f of t and y be g of t. I didn't make that explicit before, but I have now. So then this becomes the integral from 0 to 2 pi of a squared, or the square root of a squared sine squared of t plus a squared cosine squared of t dt. And that is, of course, the integral from 0 to 2 pi. We can factor out an a squared. We have sine squared plus cosine squared, which we know from the Pythagorean identity is 1. So this becomes the integral from 2 pi, from 0 to 2 pi of the square root of a squared, which is, of course, just a with respect to t. So if we take an antiderivative, we get a times t, and we're evaluating that from 0 to 2 pi. So we get 2 pi times a minus 2 pi times 0, which is, of course, 2 pi times a, which we know is, in fact, the formula for the circumference of a circle with radius equal to a. We'll do one more application. We're going to now find the arc length of the curve defined by the parametric equations x equals e to the t sine t and y equals e to the t cosine t, where t again is varying from 0 to 2 pi. So we know that this is going to be, the length is going to equal the integral from 0 to 2 pi of the square root of the derivative of x with respect to t. So we have to use the product rule there. We're going to get e to the t sine t plus e to the t cosine t all squared. And then we're going to add to that the derivative of y with respect to t. That's going to be e to the t cosine t minus e to the t sine t, because the derivative of cosine is negative sine. And then that is also squared, and that is with respect to t. So now I'm going to attempt to simplify this without running out of space. So we have the integral from 0 to 2 pi. When I square the first term, I get e to the 2t sine squared of t plus 2 e to the 2t sine t cosine t. And then squaring the last term, we get e to the 2t cosine squared of t. And I'm highly likely at this point to run out of room. Then we get, from squaring the next term, we get e to the 2t cosine squared of t minus 2 e to the 2t sine t cosine t. And you'll have to forgive me, I'm going on to the next line here. It's going to look a little messy. I get plus e to the 2t sine squared of t. And that is all under the square root, and that is all with respect to t, dt. I ran out of room, so I can't even fit the dt on there. Let me move it over. All right. Well, fortunately, some of this cancels, but the positive and negative terms here are going to cancel each other out. And we're going to end up with the integral from 0 to 2 pi of the square root of, now I have a whole bunch of e to the 2t's. I'm going to pull them out to the front. I get e to the 2t, and then I have sine squared t plus cosine squared t plus another cosine squared of t plus another sine squared of t. And the Pythagorean identity again tells us that this is 2. So we have the integral from 0 to 2 pi of the square root of 2 e to the 2t dt. And if we take the square roots, that gives us the integral from 0 to 2 pi. We have the square root of 2 times e to the t dt, which is taking an antiderivative. We get square root of 2 e to the t evaluated from 0 to 2 pi. So that is the square root of 2 times e to the 2 pi minus the square root of 2 times e to the 0. And so we end up with the square root of 2 times e to the 2 pi minus 1. Summing things up, we've seen that without needing to unparameterize our parameterized curve, we can use things like the chain rule and some algebra in order to come up with a formula for both the derivative of a parameterized curve and its arc length.